Now we've talked about the life cycle processes. We're going to talk next about requirements. One important part of designing a system is define a set of requirements that capture what it is the system is doing and how we're going to implement it. If you look at the IEEE Software Requirements Engineering Standard, it gives the following definition that's on the slide of requirement. First of all, it must be capability that's needed by a user to solve a problem or achieve an objective. In other words, we take an objective and now we're going to see, okay, we're going to add more detail on what we're going to do on the what. So what we're going to do to achieve that particular objective. And of course, when we're adding more and more detail, eventually you go from the what to the how. I mean, when we have enough detail, you're going to actually say, well, how are you going to do that exactly? Yeah. Remember, we saw before at the system level, we talk typically about answering the what question, but when we go towards the component level, we really start talking more about how exactly we're going to implement it. So, but these requirements are really kind of, and I put this on the next slide, a hierarchy of statements. We expand these objectives, these high-level objectives, and state them at a level of detail, which eventually can be implemented by a designer, a technician, etc., etc. What's very important is that this requirement is a statement of something that you actually need, a function. For example, a system requirement would give you a description of what it is that you need to do, what it is that this particular system must be doing. Besides telling you what it must be doing, you must also include some characteristics. How in terms how much of this function is needed. Now, commonly, if you look at how these requirements are written down, we use the English grammatical form using a shall. For example, when the fuel level in the tank of a car is below value X, the system shall indicate is using an L, like to the driver of the car. And how that's done can be an LED or whatever. Now, okay, why are requirements important? Requirements are really the formal language of government and a whole lot of industries when we're talking about systems. And of course, a variety of other things as well. Okay. The nice thing is that if written properly, these requirements will be interpreted the same by all parties. That means you can use them to talk about a common system that you're developing, for example, and everybody understands what it is exactly that the system shall be capable of doing. Note, I mentioned this very quickly and make it sound pretty easy. This is a pretty hard task to do, to write these requirements in such a fashion that everybody agrees on the interpretation. But you second of all want to make sure is that you get what you pay for, that what you're actually writing down, that's really what you want to have. Now, one thing, and I've talked about this before, that high-level requirements, so for example at the system level, should not impose a solution. Remember we're talking about answering the what question at the system level, but when we start adding more detail and go to the subsystem and component level, then we can start be very more specific about solutions, and then we're answering the how question. Now, it's very important to spend a lot of time up front on writing good requirements, because as we saw before in the earlier chart, if you need to change design in later life cycles, it will be very costly. Okay, so what makes a good requirement? Really, a good requirement really describes characteristics of the deliverable product of the system, things that it needs to be able to do. And you also want to make sure that these characteristics can be quantified, and second of all, can be verified. You must be able to perform a test. This test will then indicate that, okay, that your product is exactly doing what it's supposed to do. If I make a requirement that for a system that tests if your volume of fuel in your tank falls below a certain level, and then, for example, provides the driver with some kind of warning, like an LED or so, then you must be able to take that requirement and test it, And you can do this, for example, by lowering the volume in your tank and check out if the LED or whatever warning you have still comes on. So it's verifiable. Well, these requirements are typically, you want to be careful that those are stated pretty simple, that they're very positive, and that they're grammatically correct. And the biggest one of all is say, do we really need this requirement? In a lot of cases you see that people write requirements and then they add requirements to it that are not really part of what the system needs to do. They're just nice to haves. For example, maybe a GUI that's like a graphical user interface that's not required. Things may be added to the system, requirements may be added that are not needed. So good requirements stays as something that's necessary, verifiable, and attainable. Now, some problems are that, that when you start writing down these requirements, you make some bad assumptions. You assume certain things about the system or the environment in which the system is going to operate that are just not correct. If that's the case, of course, the requirements are not going to work for that particular system. Also, in the initial stages, conceptual design, preliminary design, a lot of people tend to write immediately doing implementation at that level. They answer the how question rather than just the what question. You want to make sure that you answer the what question first, and then start thinking about how to do the implementation. Okay, the other one that's a common problem is that they describe operations rather than actual requirements. Use of incorrect terms, incorrect sentence structure, or bad grammar. They're missing requirements, other requirements that are not needed, or certain requirements are over-specifying it. If you're very over-specifying certain things, you may make your system not feasible any longer. Okay, so terms that we typically use, requirements, we need to use shall, statements of facts, use will, goals, use should. Now, terms that you should really avoid are things like support but not limited to, or ambiguous terms like minimize, maximize, user-friendly. The reason for some of these terms are, and user-friendly is a good example of it, is that this is very subjective. Also, minimize, it's not specific enough. Minimize and maximize, if you get to, in that case, you already kind of, when you get from the what to the how, you need to be more specific. How are you going to do that exactly? Okay. Or you need to say to what level. Rapid is also, you really want to be more specific, how fast does it need to be? So there's a variety of different things that ambiguous terms really not give everybody on the team the same idea for what needs to be done. The other thing is like overly stringent requirements that you see on the bottom. You can specify that the area of a certain plate or something needs to be 100 square feet. Put a little tolerance in there, is probably a little bit more attainable. Now, there's a variety of different requirements. We have, like in this slide, we have the system requirements that really deal with capabilities of the system, subsystem, and component. And the operational requirements, they define the operational environment in which the system is operating. Things like the temperature, the humidity, the pressure, and potentially interfaces of the system with people. So you see, this actually talks about the operation environment. And of course, in this case, what you're really interested in is, okay, what would be the interactions between that operational environment and your system? If it needs to deal with extremely high temperatures, you want to make sure that your system is capable of still operating under these temperatures. That means they may have some cooling, or they may have some strong cases for protection, for example. Other requirements would be physical installation requirements or maintainability requirements. Now, an important one that we kind of talked about a little bit before are the safety requirements, and these really kind of define all the attributes of the system that are related to safety. So think like the reliability of the system, the availability or integrity of the system. These are all things related to safety requirements. And in the next module, we're going to talk a lot more detail about these. The next are the performance requirements. They tell you, things like accuracy, availability, continuity, range, speed, resolution, response times, everything related to the performance of the system. How good do a system need to do a certain task? Yeah. So, or how fast. It tells you a little bit about all these attributes of the system and make it useful for the customer. And of course, finally, interface requirements as well. Now, typically what we do if we talk about, if we want to describe the system, there's two requirements that are out there from the get-go, which is we call functional requirements, to identify what characteristics are requirements, so what it is that this system needs to do. For example, the launch system shall deliver a satellite to low Earth orbit, and you see in this case I use shall, it's a requirement. Whereas if you look at the second set is the performance requirement, they quantify these functions. Yeah? So you may describe first the launch system shall deliver a satellite to low Earth orbit. The performance requirements will be a little bit more specific about this particular function. So functional versus performance. Functional just describe what it does. Performance, you also quantify the details of that function. We get back to this a little bit later. Typically we can this quantitatively or qualitatively derived. This is going to be talked a little bit more when we start talking about software requirements specifically. So again, it's very important that requirements can be tested. So if you write a requirement, think in the back of your head, can I design a test for this requirement? And this is especially important when we start talking about software requirements. If you start writing down textual descriptions of what it is that your software must be doing, you must be thinking in the back of your head, can I test this? If it's a software component running on a processor that sits within a particular box, you must think, can I put the box in a particular state so I can test that this software component is really doing what it's supposed to be doing? Alright, now, so if you come to this testability of these requirements, this is related to verification and validation. When you start talking about testing of requirements, we typically mean we talk about verification, which means that whatever the results of all the process we do, the design process, so the end result actually performs exactly what is specified in the requirements. In other words, we define our requirements, and these, based on these requirements, are going to make a product. Then we're going to test this product, going to make sure that it does exactly what the requirements say it's supposed to do. This is different than validation. In case of validation, what you're trying to say is like, are these requirements that I have correct? In other words, if I do everything correct, based on these requirements, is the end product going to perform the intended function of this particular system? This is a very big difference. Yeah? So validation means confirmation, examination, and provision of objective evidence that a particular requirements for a specific intended use are fulfilled. If I implement this set of requirements, this system will perform its intended use. This is different than verification. I'll come back to this a little more later. Now, what you see in industry quite a lot nowadays is this thing called independent V&V, independent verification and validation. It really just means that if you make a product, if you have a system and you design a system and implement it, what you're going to do is you're going to make sure that the verification and validation activities are performed by an organization that has technical, managerial, and financial independence from the organization that develops it. Now, what you see is that for software independent verification and validation, the more and more companies actually doing the software independent verification and validation aspects of a particular project. And the reason for that is that the complexity and size of software is growing tremendously. If you see how much software is actually present in a regular car, or like at least in a little bit of a modern car now, it's staggering. Yeah, also what you see is that software plays a more and more role in safety critical systems. So it means for these systems it's very important that the software performs its intended function. So what you really want to make sure You can actually do in-house the verification validation, but if you do this independently, you may actually reduce the chance that there's errors that slip through. Yeah. So that's really it. The next slide is really a set of definition of terms, and these are really the terms that we defined in the last couple of slides, just summarized in one slide.